So now we can get started on defining one of the main models used in our analysis, the fossilized birth-death process. And as we saw in the introduction, two key parameters of the FBD process are the speciation rate and the extinction rate. So we are going to start by defining those two parameters. Now we want to infer these parameters during the analysis. So that means that we have to set a prior on these parameters. And we're going to choose a very simple prior, an exponential distribution with a rate parameter equal to 10, which means that the expected mean value for each of the two rates is going to be 0.1. Now these are the instructions that I used to create those two parameters. We're going to call them speciation rate and extinction rate. And as you can see, we define them directly by their prior distribution. So this is what is called a stochastic node in RefBase. So this means that's a parameter that is going to be inferred during the MCMC. And so they are defined by the tilde operator and they are assigned directly to their prior distribution. Now these parameters are going to be assigned an initial value based on their prior distribution, but in order to be able to estimate their value during the MCMC, we also need a way to change that value, of course. And so we need to define a move for each of these parameters. We are going to use a fairly simple move here because these are fairly simple parameters. They're just one value, positive, a real number. And so we're going to use a scaling move, which is called MV scale. So this move takes two parameters. The first one is, of course, the variable on which the move operates, so here the speciation rate or the extinction rate, and then a weight parameter. Now this weight is going to be defining how often a particular move is going to be used during the analysis. What happens is basically all the weight for all the moves defined for a given analysis are added together, and then a move is used in proportion of its weight divided by the sum of all the weights for all the moves, essentially. Now here, this is a reasonably simple parameter to estimate, as we said, in comparison to complex things like the tree topology. It's not very hard to mix. So we're going to set a reasonably low weight for estimating both rates. And as we said earlier, we have defined our vector of moves to put all the moves together in a U-object that can be used easily. So we're just going to append our new defined moves to that vector, both times. Now there is an alternate parameterization of the FBD process that instead of the speciation and extinction rates uses the diversification rate and the turnover. So these are also parameters we may be interested in, so we can define them in order to be able to log them and then estimate their values. However, the diversification rate and the turnover are not independent parameters. They are completely defined by the value of the speciation rate and the extinction rate, which are parameters that we have already defined. So we are not going to set up a specific prior on the diversification rate, for instance, because that value is already constrained by the values of the speciation and extinction rate. So that means that the diversification and the turnover are deterministic node, meaning they are transformation of existing parameters as opposed to new parameters. And so this is shown by the colon and equal assignment operator here. And it's the same thing for the turnover, which we can see defined here. The next parameter we want to define is the extent sampling probability, which is rho. Now in our particular case, we know rho because we know how many of the extent bare species we have in our data. So here we know that we have sampled all the extent bare species, so we have a probability rho of 1. And since we know it, we will define it as a constant node. So that's just that what that line does. And we do not need a move for that parameter because, again, it is constant. Now, we know the extent sampling probability, but what about the extinct sampling rate? Now, this parameter is psi, and it's called the fossil sampling or the recovery rate, and it's also an important parameter of the FBD process. Since we do not know this value, we are going to infer it during the analysis, and so similarly to the speciation and extinction rate above, we are going to set that up as a stochastic node. And we're going to use the same exponential distribution with a rate of 10 as we used previously. Similarly to the speciation and extinction rates, we also need a move for that parameter, and again we're going to use the same move as we defined before with the same weight. The final parameter we need to set up for the FBD process is the origin time, meaning the starting time of the full process. We are going to set a uniform prior on this origin time, with the lower bound being set at the age of the oldest bear fossil, because of course the bear clade cannot start any younger than the oldest fossil. And we're going to use as a higher bound the age of 55 million years, based on recent studies that use that as the age of the crown carnivora. Now we also need a move on that origin time, and we are going to use a sliding window move, which is a little bit better for parameters with a uniform prior. We do not use the sliding move for the rates parameter because it can create issues when the parameter reaches low values. Now here, of course, since we've defined a lower bound of our origin time to 37, low values are not going to be an issue. So you can see those two lines of command. The first one defines this stochastic node called origin time with a uniform prior on it, and then we add our new sliding move to our moves vector.